Um, uh, I think we can start. All right. So actually, I'm assuming that you all gone through the week two lectures.
Yes, sir.
So um, it's not a problem. We will. It's better to go through it again. Um, right. I think there's a issue. Anyway, so do you guys have any doubts in previous session? Uh, ask me now. Um, Maybe I will give you 1 or 2 minutes to. Last session was we were able to develop solving a Navier-Stokes equation for a simplified flow problem, which is flow between parallel plates equation, and we were able to simplify it using some assumptions, and we were able to get some velocity profile as an end result. But we also understood that such kind of flow may not occur in real world, and you may also need to solve the whole Navier-Stokes equation to predict any real world. Solving an Navier-Stokes equation analytically is not possible. That's why we need to use some numerical methods, numeric discretization schemes to um, differential equations into algebraic equations, and then we should solve it. So that's how we will be that is what CFD actually is. So um, let's go ahead. In the main chunk of the week 2 was discretization. So this discretization is basically on finite difference method. So what discretization actually means is you are trying to um, approximate a derivative, a first based on the function values. Like it can be found where get that value. Like without differentiating a function, how can you get that is approximate um, uh, for a real derivative. It is not exactly the derivative. So if you differentiate it, you will end up with a, but without differentiating, how you are getting the same results or approximate results, what discretization is. So we won't go into the details of discretization or each and every scheme. I will just show you how to develop a scheme, discretization scheme for order derivative. So first order derivative, we are going to develop a discretization scheme. Um, Going to do a second order accurate scheme. We are going to develop a second order accurate scheme. So one of your graded problem, if you check, one of your graded assignment is going to be this second order accurate backward difference scheme. We won't be because derive it in a different way, but I will give you a glimpse. Here the scheme would be a little bit different. You will come to know soon. So statement is we have a function phi, a polynomial function. We need to find the value of this function at x equal to 1.6. Okay. So here we are going to take the step size of uh, here we are going to take the step size of delta x to be 0.02. Um, uh, so since it's a polynomial function, you can easily differentiate it and you can get the value at x equal to 1.6. But we are going to use some discretization schemes to uh, get this value without differentiating. So let's start. So first, it is important to find a stencil. Like what is if you are let's say finding a discretization scheme. If you are developing a scheme, first you should understand, like, with the help of how many nodal points you are going to take to approximate a derivative. Okay, so stick to backward difference. So the backward difference is nothing but, let's say I is our point of interest. So from I, from the backward or negative side is going to be backward difference, and the positive side will be forward difference. Okay, so we will stick into backward difference. You can construct a scheme with which has both these two, which you might already know. You might have already the lectures too. So we are going to you can construct schemes with from here to here. So here there will be I plus 2. So here to here you can construct a scheme with that also. With this also you can construct a scheme. With this it's going to be backward dominated scheme if you construct a scheme from I minus 2 to I plus 1. So you can construct any way you want. There is no rule to construct only with this, but the consequence would be different based on different schemes. So we will stick to backward difference. Let's say we will consider. Of course, you can consider with only these 2 points also, but we will construct with the 3 points. Let's see how it is going to happen. Okay, so backward difference or upwind differencing, both are same actually. You can the uh, terms are, you know uh, changeable. Uh, so if you are solving a fluid flow problem, let's say the flow will be going from I minus 4 to I, so then it becomes like upwind, like it is going from we are in I. So similarly, if you have a flow from, if you construct a scheme from I to I plus 2, the from I the flow is going to go in this direction, so it is going to be downwind. If a flow is like this, the arrow would be upwind and the other end would, so, so if you the backward is also called as upwind scheme, and forward is also called as downwind schemes. Mostly we use backward schemes that you will know later in the while the course progress. So let's get started. If you guys have any doubts, you can stop me at any time, and you can ask the questions. Uh, so I hope there is no questions. I will go ahead. All right. So basically, to construct any scheme, you need a Taylor series expansion. So you all know what a Taylor series is. If I want to simply explain or tell what is Taylor series, it's just you want to find a function at some x by knowing. So by knowing the value of function at x naught and the distance between x and x naught and its derivative at x naught. So if I want to simplify and write, you can let's say I am plotting a function. Okay, so a function can be any curve, like let's say it is a, so let's say this is phi and this is x. So based on x it varies like this, but only thing we know is let's say this is x naught. Okay, so at x naught we know phi of x naught, number one. And we also know phi dash of x naught, phi double dash of x naught, so on and so forth. We know all these derivatives at the x naught. Okay. And if you want to find what is phi at some x, let's say this is x. So you want to find function at x, but you don't know the function value, you know the function value and its derivatives, and you also know x and x naught difference. So with this, if you want to find the phi of x, you should go for Taylor series. So that's what Taylor series tells. So a phi of x is actually phi of x naught plus x minus x naught times derivative of x naught, and similarly so on and so forth. It's if you want, you can go and check the um, how is this theorem possible, like go and check the proof of this theorem basically. So we will construct any scheme based on this Taylor series expansion. um, so why we need to choose Taylor series is we need to find derivative at this point I, and we at these points, but the derivatives at those discrete points, but we don't know the function actually. So that's why we go for Taylor series. That's why Taylor series is relevant to discretization too. So let's say I'm applying so how we will start. So do you guys have any idea like how to start how to develop a discretization scheme? It's actually basically simple. What we will do is we need to find Taylor series for the points of interest. So let's say for us right now the point of interest is these things. So we are going to construct a backward difference scheme, and we will use all these 4 points. This is our point of interest. Based on the values of this, you need to find the derivative of so how are we going to do is we just need to apply Taylor series for I minus 1, I minus 2. So how are we going to do this? So let's say you are applying at x equal to xi minus 1. Okay. So apply Taylor series for this. Phi x will be x minus 1. So it will be f of phi of x minus 1. This will be equal to, now one more thing is we will consider x naught is actually xi. So what happens, this will be phi of xi plus xi minus naught, sorry actually xi minus 1 times xi into phi dash of xi plus xi minus 1 minus xi whole square by 2 factorial phi double dash of xi plus, be like this. Now let's use some notations to simplify and write it in a very elegant form. If we write like this, let's say phi of xi minus 1 is just simply phi of I minus 1. Okay. And then phi of xi is actually phi I, and means xi minus xi minus 1 is equal to delta x. Similarly, xi minus 1 minus xi minus 2 will also be delta x. Xi minus 2 minus xi minus 3 will also be delta x. So the spacing is uniform. Um, so uh, so the spacing is uniform, like it's not varying. So if we consider that xi minus 1 xi is going to be minus delta x, because xi minus xi minus 1 is delta x, and x, let's write it like this: dou phi by dou x evaluated at I delta x the whole square by 2 factorial dou square phi by dou x square evaluated at I plus minus delta x cube by 3 factorial dou cube phi by dou x cube evaluated at I plus series goes on. So uh, if we look at this, this is evaluated at xi minus 1. So let's say similarly we will write it, let's make it more simplified. Phi I minus 1 would be delta x dou phi dou x at I evaluated at I plus minus delta x square is going to be delta x square by 2 factorial dou square phi by dou x square evaluated at I minus delta x cube by 3 factorial dou cube phi by dou x cube evaluated at I plus dot dot dot. So it's you can see that this will be an approximation for phi I minus 1, knowing that phi like phi I and dou phi by dou x and all the derivatives at I we know. So similarly if we apply let's say at x is equal to xi minus 2. So can you guys guess what would be the answer? Phi I minus 2 would be
Phi I minus 2 del x del pi by del x I minus 2 del x del pi by del x I and plus 2 del x whole square by 2 factorial dou square pi by dou x square I. Something like that. Dou square pi by dou x square I minus 2 del x whole cube by 3 factorial dou cube pi by dou x cube I that I.
so this is for I 2. So let's say let us simplify this also a little bit, which would be easier for us for calculations. Phi I minus 2 would be phi I minus 2 times delta x dou phi by dou x at I plus 4 delta x square by 2 factorial dou square phi by dou x square at I minus 8 delta x cube by 3 factorial dou cube phi by dou x cube I plus dot dot dot. So let's say let's write the same thing for equal to xi minus 3. What is the-
Phi I
1 second, Divakar, sorry for that. There is a question, why can't we go for phi I minus 1 plus dot dot dot? Your questions, can you tell me what is your question? Possible, can you unmute and ask? Uh, I couldn't hear you, Sam. Can't we go for phi I minus 1?
Yes, sir. You mean to say that instead of pi I, why can't we use pi I minus 1, something like that, I think, sir.
Right, right. So you are telling why can't we take x naught to be xi minus 1, is it? If you take x naught equal to xi minus 1, then phi I minus 1 would be, yeah, you can do that. You can still go for that and you will end up with the same results. You it as a homework, or you try to use it with phi I minus 1 and you will end up with the same results. So, session or so, you will end up with the same results for sure. Uh, if you have any doubts again, you can again ask me in the next session. So if you go for phi I minus 3, this would be, go ahead. You were saying something.
Pi I minus 3 del x, del pi by del x, I.
Go phi by do x at I, okay.
3 del x whole square by 2 factorial, del square pi by del x square at I.
Square by 2 factorial, dose square phi by del x square at I. Then,
My minus 3 del x whole cube by 3 factorial, del cube pi by del x cube at I.
right, 3 factorial del cube phi by del x cube at I plus dot dot dot. Right. So similarly, we will simplify this also a little bit. Phi I minus 3 would be phi I minus 3 delta x dou phi by dou x at I plus 3 square would be 9. 9 delta x whole square, 9 delta x square divided by 2 factorial, dou square phi by dou x square evaluated at I minus 3 delta x. So would it be, sorry, so 3 cube would be 9, 9 3s are 27, 27 delta x cube dou cube 5 by dou x cube evaluated at I plus dot dot dot. Alright, so this is your third equation. Now you can construct the scheme with these three equations in n number of ways. Like, there are a lot of possibilities that you can construct. Let's say, let me write it down separately. So here you can see we have three equations for three nodal points in terms of phi I and derivatives at phi I. So what is our interest? What is our interest is to find first order derivative, right? Right. So that is our goal. We need to find that. So we can rearrange the equations, we can add, subtract, and we can end up with some scheme. But what is the catch here is, we need to develop second order scheme, second order backward difference scheme. So these are, we considered our backward difference points. These are backward difference points, nodal points. So this is going to be a backward difference scheme, and now we need to make sure that whatever scheme we construct should be a second order scheme. So you guys want to guess how we are going to construct this second order scheme. So what do you mean by second order?
Error will be in second order, sir. Am I right?
And
Second order means error will be in the second order or what, sir?
right, right. So you are almost there. So second order means um, numerical and numerical. If the delta x is reduced by half, the second order means the error would be reduced by 1 by 4th. So we will see that in, uh, in some 10 or 20 minutes after constructing the scheme. We will see that like for the same function phi I, we will consider different delta x. Okay, when we reduce the delta x, like let's say 0.02, when you reduce it by half, the delta x, let's say 0.01, what happens, the error becomes 1 by 4. That's the second order. First order scheme means error also reduces by half. Second order scheme means error reduces by 1 by 4. So we will see that when it comes. So but when you want to construct, how do we know that to make it second order? So one more thing here is this, if it's a second order scheme, the truncation term, the term we have no here, dot 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 dot, those things are called truncation term. We are not interested in all those derivatives, and or we can say that those are very less, like very less weightage to the main value you are finding. So those truncation term, the order of the truncation term also it's called as a second order. Like the if the truncation term is in the uh, say delta x, in the order of delta x, then it's a first order again. If the truncation term is in the order of delta x square, then it's a second order. So similarly here we need to find dou phi by dou x in terms of these things. That is a second order. So one way to easily construct this is, so here we have delta x. Let's say you divide it by delta x. What happens? So this would be divided by delta x. This would be divided by delta x. This term also, I mean every term would be divided by delta x. Now term will have a order of delta x. Term will have a order of delta x square. Construct a second order scheme. You somehow have to eliminate this term. So you somehow have to weight these equations and add such that these three terms cancel out each other. Then your scheme automatically becomes a second order because the truncation term is dou square, dou cube, dou cube phi by dou x cube. It's actually, it is in the order of delta x square, which means a second order accurate scheme. So if you are able to, remove these three terms while adding these three equations, you will end up with the truncation term having order of delta x square. Then your scheme automatically becomes, what do I say, second order accurate. So let's add these three equations. Let's see how we can do this. How we can, all these three equations such that it becomes a second order. Let's say this is first equation, second equation, this is third equation. Okay, so can we weight this equation? We somehow have to, um, this is 9 delta x square by 2 factorial. This has weightage of 4 delta x square by 2 factorial. This has weightage of delta x square by 2 factorial. So we somehow have to come up with the uh, formula such that this delta x square cancels out. So can you guys guess what would be?
Divided by del x square by 2 factorial.
del x square by 2 factorial would do, but this has this equation has 1, this equation has 4, this equation has 9, right? How are you going to negate it also? Say you are just simply subtracting these three equations. What happens? So this would
Yeah.
be 9 minus 4 would be 5. 5 1 would be 4. Still there is some term is there now. Say you multiply this by 2. Now what happens? So this term would be 9 delta x square by 2 factorial. This term would be 8 delta x square by 2 factorial. So 9 minus 8 would be 1. Uh, then this term is already delta x square by 2 factorial. So, so we can easily eliminate these three equations. Let me write it down and show you. So, we are taking this 5I minus 3 equation. So LHS we will add it separately, RHS we will add it separately. This is 5I minus 3 minus 2 times 5I minus 5I minus 1. This would be for third equation, it would be 5I minus 3 delta x dou phi by dou x at I square by 2 factorial dou square phi by dou x square at I minus 27 delta x cube by 3 factorial dou cube phi by dou x cube evaluated at I plus dot dot dot, and then minus 2 times the whole RHS of second equation. What would be 5I minus 2 delta x dou phi by dou x at I 4 delta x square by 2 factorial dou square phi by dou x square at I minus 8 delta x cube by 3 factorial dou cube phi by dou x cube at I plus dot dot dot. Okay. Now minus the first equation. First equation is 5I minus delta x dou phi by dou x at I plus delta square by 2 factorial dou square phi by dou x square at I minus the factorial dou phi by dou x cube at I plus dot dot dot. Alright. So if you see here, plus 9 delta x square by 2 factorial, right? And this is going to be minus 9. 9 minus 9 is 0. So can I strike this all three?
Yes, sir.
So strike all these three. What would be the final solution? So 5 I minus 2 minus 5I minus 1 is equal to, how many times 5I is there? 5I minus 5. How much is this? So similarly you can strike 5I and minus 5I, and so at the end you will have minus 2 5I, right? And you can see that minus 3 delta x, let's write for dou phi by dou x at I. So it has minus 3 delta x, and minus 2 into minus 2 is minus 4 delta x, and so 4 plus 1 is 5 delta x, 5 minus 3 is so it would be delta x, right? So this term we can simply represent it as like this, like order of delta x cube. Okay, let's not do that now. Maybe we can write it whole. Uh, Dou cube phi by dou x cube at I into, so 1 by 3 factorial is common for everything. So this has similarly delta x cube is also common. So this term has minus 27. This term has let's write it down, minus 27, and this term has minus into minus plus 2 times 8 is 16, so plus 16, and this term has minus into minus plus 1, right? So let's simplify this equation also. Phi I minus 3 phi I minus 2 minus phi I minus 1 is equal to minus 2 phi I, okay, plus dou phi by dou x at I into 2 delta x plus or minus 10 delta x cube by 3 factorial dou cube phi by dou x cube at I, plus there are few other terms are there. So what we can do here is, where truncation comes, so what we can do is, we will not consider this part of the equation. Okay, so we will just replace this part as order of, so there's some um, term is there which is of order delta x cube. So that's what we are telling. So we the order is actually written represented like this, order of delta x cube. So if you, and other all other terms are going to be less than delta x cube, like delta x power 4, delta x power 5. So we are not interested in those. So only the immediate truncated term is going to be in the order of delta x cube. Okay, so if you are simplify it, let's say you our main goal is to find dou phi by dou x. Let's take it to the one side. Dou phi by dou x at I would be equal to, this is positive, let's keep it there, let's take everything on the other side. Phi I minus 3 minus phi I minus 2 minus phi I minus 1 plus 2 phi I, alright, delta x plus, there is this order of delta x cube times delta x, right? So this order of delta x cube is nothing but, let me write it explicitly. So order of delta x cube is nothing but 10 delta x cube by 3 factorial dou cube phi by dou x cube at I plus whatever the term. So let's say you are dividing this order by delta x cube. Okay, so if you divide this order by delta x, what happens? It's going to be the order of, so let me write it down here again. Dou phi by dou x at I equal to phi 2 times 5 phi I divided by plus order of divided by delta x would be delta x square. So this is going to be your final for approximate for dou phi by dou x. Is there? Do you have any questions? I see your hand is raised.
No.
Okay,
Hello,
okay, okay.
sir. I wanted to ask regarding that finite difference method. Means like finite difference method using polynomials part. Means like I am not able to understand that higher order difference and some first and second order. Means like I am a little bit confused about it. So could you please explain about that part?
Okay, so uh, you understand the polynomial fitting method, the other one, that one? Actually, what do you want? Like higher order schemes or higher approximation?
Yes, sir.
Okay. So yeah, we will come to that. We will come to that. I will spend some 5 minutes or so. If not, I can also provide you some notes, or maybe next session also I can derive it. First, let's finish this. Um, so is that fine?
Yes, sir. Okay.
Okay. So is this clear? Like I have. Let me write. So this we have written it. So this is our final equation. This we can also write it like this: dou phi by dou x. It's actually approximately equal to phi I minus 3 times phi I minus 2 minus phi I minus 1 plus 2 phi I divided by 2 delta x. So I have removed the order of delta x square term, and I'm telling that the dou phi by dou x is approximately equal to this whole term. So this is how you construct any scheme actually. So this is a second order scheme because the truncated term, the first truncated term is in the order of delta x square. So it is a second order scheme. Number one. So but you have not developed this scheme, or someone else did the scheme, and you have only final form of the. Have any thoughts? So if you haven't derived all these things, you the order of truncated term.
Since
Then you, yeah, go ahead.
since phi I minus 3 term is existed there, we can think it as actually del x cube. So by del x actually we can generally it will come because of pi I kind of del pi by del x left side is there no, so obviously the del x will be exist. So we have to send this del x division we need to do in that manner. Second order we can assume like we may get some idea like that.
So whatever you said is fine, but you can't actually randomly guess like that. So you need to know first order scheme is second order or first order. So one thing is we should go back to the basics, or we should go back to the definition of order. So at the start of this session I told you that um, the order is nothing but if it's a first order scheme, if you delta x, like if you um, the delta x is 0.02, and if you uh, divide the delta x by 2, your error will reduce by 2 if it's a first order scheme. If it's a second order scheme, when you reduce the delta x by 2, the error will reduce by 1 by 4. So let's see that, like let's assume that we haven't done anything like this. By the way, this derivation is clear, right? Everyone understood, right? We will discuss about order now.
Sure, yes, yes.
So I assume that everyone understood that. If not, you can ask me questions. So let's say this is your scheme, final scheme, but you don't know the truncated error. Let's first try to solve our problem. So this is the problem we have. Let's use this. Let's use this scheme to find dou phi by dou x at I. Here I would xi minus 1. So how will you say that? Let's say, let me write it down. Um, uh, Phi of I minus c. So we know that I by dou x at any I x equal to xi. Let's say at I is, I actually replaced that x equal to xi, right? So this is actually equal to phi of I minus 3, phi of I minus 3 minus 2 times phi of I minus 1 and minus phi of I minus sorry, I minus plus 2 phi I divided by 2 times delta x, right? So here now we are going to take xi is equal to 1.6 and equal to 0.02. Can you guys calculate phi I minus 3? It's actually phi at x equal to xi minus 3, which is phi into xi minus 3 times delta x, which x equal to 1.6 minus 3 times would be 1.54. So you just need to substitute this 1.54 in this equation to get the value. Can you guys tell me the value? Quickly calculate it. So I need these four this have calculators with you. Are you guys calculating? So in the interest of time, I'm just giving you the values which I already calculated. Kindly go and check. Um, 3 would be 12.22316, 12.517112, 12.816. So let's say with the help of this, I'm calculating dou phi by dou x at I, which is actually x equal to 1.6. I just need to use this value to put it here, and delta x is 0.2. So if I do that, my answer is 15.0792. So if you just want to do it analytically, let's say because here uh, here the function is polynomial. You guys know how to differentiate a polynomial, right? So what would be dou phi by dou x? Here it's actually d phi by dx. Anyway, so what would be dou phi by dou x? square plus 4x plus 1, right? Q would be 3x square, 2x square would be 4x plus 1. So if you substitute equal to 1.6, let's say, if you substitute here, what happens? The answer would be 15 point. So you guys can easily compare these two. So the scheme we developed and 15.08 is the actual answer. So you see how close we are. So now what if we we take delta x to be zero point 0.1? At x equal to 1.6 when equal to 0.01. So you guys can calculate it separately and you will see that what is the error actually? The error is going to be the 792 minus 50 for delta x equal to 0.02. Similarly, you find the error for delta x equal to 0.01. Okay, for this and substitute here and you compare these two errors, you will end up getting the error will be one fourth of the previous error. So I've developed like a program for this simple program. So I guess you guys can see my screen. Can you guys see my screen?
Yes, sir.
Okay, 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 okay. Thank you. So this is the function we are solving for. Okay, and let's say my dx equal to 0.01, right? What was the dx? 0.02. Okay, so we see that this is one of the scheme which I already developed. So if we look at this is the function handle, and I this is the equation we developed now, and with the help of this equation I also found d square phi term, which you can also do it. It's not a big thing, but just for showing I just added that also. So anyway, so if we look at 0.02, you see the analytical results are 15.08, right? And you our error is 0.02. Let's say you are reducing it by zero point 0.1. Okay. So what happens? Error is 0.005. So at here the error was 0.002. It becomes 0.0005. So it's actually you are actually dividing this term divided by 4. This that it is a second order scheme, right? So this is what second order scheme means. Like let's say if you are finding, let's say delta x is 0.1, okay, the error is 0.05, right? So analytical is 15.08 and numerical scheme, whatever scheme we develop, is 15.0. Change this zero point 0.1 to 0.05, which is half of delta x. Zero point 0.1 divided by 2 is 0.05. If we change that, the error is 0.0125. So before it was 0.05 and it is a second order scheme. So that's how you will know that by evaluating some functions at let's say two different delta x or three different delta x, you will see that it is going to be first order or second order. That's how you will find it. If you don't know how people derived it or how the scheme was derived, and if you don't know the truncated term, this is how you will find the for point 1 we have 0.05. So if you make it 0.05 here, what happens, 0.05 becomes 0.0125, right? So if I make it if I divide this also by half, what happens, 0.0125 becomes divide by 2 and divide by 2, 0.0003003125. So here only few terms are there, maybe 125. So you see that it is the error gets separated by, I mean divided by 1/4. So that's how you will find it's a second order scheme or not. All right. Um, guys, understood what I'm trying to say?
Sir, actually, I got one idea. I mean, a doubt actually. I'm having one doubt. So, when we have to use this forward difference method and the backward difference method, so specifically, can you tell me, like, where we supposed to go ahead with what action? Thank you.
So actually, that would be covered in coming lectures. So quickly, what I can say is usually when the flow is flowing from one direction to other direction, at that time you should also let's say flow is flowing in this direction. At that time, here it's I and here it's I minus 1. You need to choose a upwind scheme or backward difference scheme by doing this. So if you have a heat diffusion problem, heat diffusion doesn't have a direction. It diffuses in all the direction. That's the part of heat diffusion. At that time, you should go for central differential. So it would be weighted. So these things you will learn soon in the upcoming course. Like, you will also know what if I for an flow, what if I choose I and I plus 1. You see, you are finding the derivative. uh, it doesn't make sense, like flow is coming from upwind, but if you are taking a downwind, so it's basically a little bit common sense and little bit practice will uh, like which scheme you need times. Number one. And while selecting a scheme also, you might end up getting some unphysical oscillations. Like if you select a higher order scheme, you will end up getting unphysical oscillations or unphysical solutions. So at that time you need to discretize it even more. So there are a lot of parameters which you need to take care, and it will be soon you upcoming weeks. So you don't need to worry about that. Only thing for now you should know is like what is this order, like what is the physical significance of order, and the discretization schemes are happening, like how it is. So here, for example, if you take the phi of x's, we know it's a polynomial function. Okay, so but in yes, there is a function only. What is a function? What is a polynomial? Polynomial or trigonometric or whatever. What is that? We don't know that in a problem. So at that time, what you factorization schemes will help you. Let's say if you want a derivative, you can get the derivative by knowing the values surrounded by it. And these factorization schemes will help you to construct a system of linear equations, linear algebraic equations equal to b, and you can solve it like taking a inverse, x equal to a inverse b. So those things will come in the future, in the upcoming weeks. I will also derive and show you everything, but for now, is this clear, the order and I see. Because in the grading assignment you are going to have a uh, few schemes, like you need to find which scheme is that, which order is that. So for that, you need to know. That's why I thought I will show you some examples.
Yes, sure, we understood. Thank you for it.
Okay, all right. So yeah, by this session, if you have any doubts, you can stay back and ask. And coming back to so anyway, whatever he asked. Anyway, yeah. Can we have access to these notes? Yeah, sure. So I will upload both these notes and my MATLAB program also. It's a live script program. Uh, uh, you can access it if you make it your own scheme. You can put it in the script and you can check the order of accuracy there. So basically, from this exercise, what we can understand is, um, if you your mesh, like it's basically a mesh. If you go back, the stencil we consider, we call this as a stencil, or we call this as a grid, we call this as a nodal points, like all these things are there. But basically, the if you consider a delta x to be very less, you are going to get more accurate result. So that's why people usually go for fine mesh to get accurate results. So basically, the essence comes from here, because the discretization means when you reduce the delta x, your error is going to reduce. And if it's a second order scheme, it's going to be even more helpful, because error is going to be reduced by 1/4. That's the basic idea of making a fine mesh and getting a more accurate solution. So yeah, so by this I will conclude. If you have any doubts, you can stay back and ask, not a problem.